In this video we're going to be looking at building a smart telescope. The first step was to connect a computer to your mount and camera. This can be a laptop on your knee outside next to your telescope. Or it could be more remote, in which case you would need a mini computer on your telescope and you'd control it wirelessly from a desktop or mobile device. And the wireless, some mounts come with a hotspot wireless, or you could use your home network if it reaches that far out. These are three of what I believe are the most popular mini computer options. There's the ASI Air, Stellarmate, or a Windows based system. So we'll do a very quick and basic comparison of these three. The first is the ASI Air, which is made by ZW, a large astronomy manufacturer. Most connectivity is limited to ASI ZW brand, but this makes for trouble-free integration of equipment. In contrast, Stellarmate will connect to almost all astro equipment. It's made by Icarus, who are an astro software company, and it's sold either as a downloadable Linux-based operating system and software package that can be installed on something like a Raspberry Pi, or it can be bought as an off-the-shelf computer with everything installed ready to go. Or you could go for a Windows-based system such as NINA, which is Nighttime Imaging and Astronomy. It's free open source software that will run on any Windows 10 or 11. All three options provide the same basic functionality, which is connection and control of mounts, cameras, and a host of additional peripherals. Data capture and image viewing, including stretching and live stacking. Integrated with Planetarium software for target selection, and we've looked at Planetarium software before. A database of targets and their availability at your given location. Plate solving to confirm target acquisition. Support for polar alignment. Scheduling so the telescope can be left alone to capture multiple targets. Integration with other astronomy software such as Planetarium software and something called PhD2. We'll talk about that later. And some come with power outlets for your peripherals. This list is far from exhaustive, and additional functionality is added via updates. Let's have a look at how this all comes together on my smart telescope. First, we have the equatorial wedge, which has transformed my AZ mount into an equatorial mount. Notice at the front there are two black knobs. They're for fine adjustment in the declination, and at the back is a larger black knob, and that's for fine adjustment of the altitude. Fastened above that is the go-to mount, and this one comes with the option of being controlled either via Wi-Fi or a USB connector. It's important with any telescope to correctly balance it. This is done with a counterweight, and what I've got here is a homemade job, which is a threaded bar connected to a block of wood with some lead weights either side, and shortly I'll be connecting on top of that the mini computer and its battery. The OTA is a 72mm refractor, which has a focal length of 420mm and an f-stop of 5.8. The white part at the top is a dew shield which can be screwed off for easier transportation. Strapped around the dew shield is a dew heater, and that's powered by the black box you can see just above, which is a rechargeable battery. At the end of the OTA train is my DSLR camera. There's an adapter then that connects to a field flattener, which is used to bring into focus the outer rim of your image. And within inside all of that, I've got a CLS City Light Suppressor filter. On the focusing knob, I've got what's called an EAF, an electronic automated focuser. On the side of the OTA is bolted on a guide scope, and the red bit at the front you can see is a do-it-yourself 3D printer dew shield. And finally, at the back of the guide scope is my guide camera, which doubles up also as a planetary camera. And here is everything connected up together. So I've got a mini Windows 11 computer, and that's connecting to the mount, to the EAF, to the guide camera, and also to the DSLR. So night has arrived, and I'm going to connect to my mini computer using remote desktop. I'll open Nina and select my previously configured profile for the Canon and my 72mm refractor. Just for clarity, this is not a tutorial on how to use this software. I'm merely just explaining what I do to get an imaging session going. So the first thing I'll do is connect the camera, then the focuser, then the telescope mount, and finally the guide camera. The next thing I'll do is go across to the image menu and open up the image screen. And then the first thing I'll do is I'll set it for a 3-second exposure. And if you look down to the bottom left, you'll see the exposure being made, and then it will say debaying, and then it will say stretching. I've got to warn you, this is a very cloudy night, and I'm looking at Polaris there, and you can see the sort of haze around that bright star. So the next thing I'm doing is running an autofocus session. I'm going to speed this up, but what it's doing is taking multiple shots at different settings for the focuser to determine which is the best setting. So over in the top left hand corner you'll see the EF settings change, and over on the right a graph being drawn for the settings versus the what's called the HFR, half flux radius, which is a measure of the sharpness of the image. And unfortunately the clouds have beaten me here, and the last image is way off, so it's done the job, but I would have preferred it to have made a nice U-shape or V-shape curve. I'm going to polar align the telescope, and I'm using something called 3-point polar alignment. So this system takes 3 separate images, and after each one it will attempt to plate solve it and then change the angle that it's looking at the target and take the next image. When it's successfully taken 3 plate solved images, it will calculate how far the telescope is out of alignment. Once I've got those measurements, it's a case of going outside and adjusting with those black knobs that we saw before the azimuth and altitude until I get to I like to be within 1 arc minute. You can see the total error is over 28 arc minutes. But because the cloud is moving in so fast, I'm going to leave it at that. I would now normally go and set up the guiding, but I'm going to skip that stage and go straight to selecting a target. Now I could use coordinates from something like Telescopius, or I could link into one of the planetarium pieces of software and drag the coordinates across. But I'm not. I'm going to use the built-in Sky Atlas that comes with this piece of software. So over in the left-hand corner, I'm searching for M31, the Andromeda Galaxy. As you can see, I've already inputted my local horizon, and what this is showing me is that Andromeda isn't available because it's below my horizon. So I'm just going to go now and just search for M, which is M for Messier Catalogue. And I can scroll down and see what's going to be above my horizon now. And this looks like an interesting target. It's the Veil Nebula. So what I'll do is add it to the framing assistant, whereby based on the size of my sensor, the pixel size and the focal length of the OTA, it will slew to the target. It'll take some images of it, and using plate solve it will keep moving the mount until the target is centered. Then I can adjust the rotation of the camera to what I want, and I can also just slightly adjust the frame so that it's going to give me the image that I desire. The whole process takes a few minutes, so I'm going to speed it up. So once I'm satisfied with the framing, I can go over to the sequencer and I'll tell it that I want to take 20 images of 120 seconds. Two minutes later and the first image has arrived, and if I zoom in you'll be able to see that the stars have become elongated, and that's because I haven't set up guiding. So I'm going to do that next. So this is a piece of software called PHD2, stands for Push Here Dummy. I've already calibrated it, which took about 5 minutes. I've selected a star, and so the system is taking an image with the guide scope and camera about every 1 or 2 seconds. It's measuring how far away it is from the target star and moving the mount accordingly. And as you can see, the graph that it's producing is also replicated within the Nina application as well. So we've now got the first image back using guiding, and the stars are a lot sharper. If you look at the bright star just to the right of it, you might be able to see a very faint line, and that's the beginning of the Veil Nebula. And it's not until we have taken all the images and then gone through post-processing will we actually see the nebula. to our final challenge, which is choosing if you want to go smart, and if so, which computer system will you use? So in the next and last in this series of videos, I'll wrap up with some details of accessories that you can buy for astronomy, and we'll see how the Veil Nebula turned out.